A simply supported steel joist of 4 meters effective span is laterally supported throughout, and it carries a UDL of 40 kilonewtons, which is inclusive of self-weight. Design an appropriate section using steel of grade 410, right? So here the question is very clear that it's a laterally supported beam, right? So from this you can say that you are going to design a laterally supported beam. And here one thing which you have to focus is the load UDL is not given in per meter length. So it is not 40 kilonewtons per meter. They have just said the intensity of the load is 40 kilonewtons. That means you have to find out what is the uniformly distributed load per meter length. Okay, that is one thing. And here you have to design an appropriate section. So when we are discussing in the last class, the appropriate sections for the beams are I sections, right? This is what we have discussed. So the appropriate sections for the beams are I sections. Don't go for the selection of any other sections except I. Okay, so this is the simple data that is provided in the question. So let's write the given data initially. Okay, so given, so the effective span of the steel joist, that is L equals to 4 meters. So this is the effective span. Okay, and it carries a UDL of 40 kilonewtons. Remember, this is not the load which is given for per meter length. So therefore the value of capital W is given as 40 kilonewtons. But what you have to find out, you have a simply supported beam on which an UDL load is coming. That means you have to find out the load value per meter length, right? So how to find out the load value per meter length is W equals to, okay, small w, which is the intensity of the UDL load. Small w equals to capital W upon L, where capital W is 40 and the length, that is the effective length, is 4 meters. So upon 4. Okay, so this will give you the intensity of the UDL load, which is as 10 kilonewtons per meter. Remember, don't directly take the value of 40 kilonewtons as the intensity of the UDL load. No, it is not the intensity of the UDL load. So the intensity of the UDL load has to be calculated in this way. That is small w equals to capital W by L. Or you can make here one statement that intensity of load W equals to capital W by L. Okay. Now we need to find out the factored load. So factored load equals to factored load. You can make it as WU. Factored load equals to 1.5 times of 10, which will give you 15 kilonewtons per meter. Okay. So from now on, whatever the load that you're going to take or you're going to consider, it must be a factored load only, not the intensity of the load, which is W. Okay. Anyways, so the first step which we are going to solve is you need to find out the factored bending moment and the factored shear force, that is maximum bending moment and maximum shear force. So let's find out the bending moment and shear forces. Shear force actually. So the bending moment is denoted with the symbol capital M. Okay, you can make it as maximum bending moment, capital M, equals to, you know the formula, when a simply supported beam carrying UDL load, the maximum bending moment formula is WL square by 8. This is the formula. So where W is 15 kilonewtons per meter, which is the factored load intensity, into L is the effective length, which is 4 meters. So 4 square upon 8. So if you solve for this, the bending moment, or the maximum bending moment, will be 30 kilonewtons meter. Okay. Similarly, you also have to find out the value of maximum shear force, SF. So which is denoted with the symbol capital V. Okay. So you know the formula. I mean, I guess you have an idea about this. The maximum shear force for simply supported beam carrying UDL is W L by 2, right? So this is a formula to find out the maximum shear force, where W value is 15 and the effective span is 4 upon 2. So which will give you again 30 kilonewtons of load. So now you have got the maximum shear force and the maximum bending moment values. Now what you have to do in the next step? You have to find out the values of ZPZ, right? That is plastic section modulus. So let's keep this heading, that is plastic section modulus. Plastic section modulus required. Let's keep it as required only. Okay, that is ZPZ required. So plastic section modulus is denoted with ZPZ, and you need to find out the required plastic section modulus. You don't know what is the exact plastic section modulus. So the formula for this is M into gamma M naught by Fy. So this is the formula which we have said, right? So what is the M value? It is the maximum bending moment, which is 30 kilonewtons meter. So I'm converting that into Newton mm. So 30 into 10 power 6 into gamma M naught is 1.1, which I have said in the previous class. And the value of Fy is 250. So you have got the value of ZPZ required as 132 into 10 cube mm cube. Okay, so this is the value of ZPZ required. Now the thing is, you have to select a I section. Okay, you have to select an I section based on the ZPZ value. Okay, you have to select an I section based on the ZPZ value. Now let's write this statement. Selecting an I section based on ZPZ required from where? From annexure H of IS 800 2007. Now open IS 800 2007 codebook and go to the annexure H, which will be there in the very last pages. Find out a section which has a ZPZ more than 130 into 10 cube mm cube. Okay, I'll repeat the statement. Now you need to find out a section which has a ZPZ value, that is plastic section modulus value, greater than 132 into 10 cube mm cube. Okay, now open that and find out the value and let me know what is the section which you are going to select. So before selecting the section, I just want to indicate that in the last class we were discussing that if you are designing the beams, okay, if you are designing the beams, you have to consider the three sections. One is ISLB, and the second one is ISMB, and the third one is ISWB. So if you are selecting a sections, it must be one of these sections. Okay, it must be one of these sections. It can be ISLB, sorry, yeah, it is ISLB. It must be from ISLB or ISMB or ISWB. So the selection of the section depends on the value of the ZPZ value. Okay, that is 132 into 10 cube mm cube. Okay, now let's find out the section. Yeah, so this is the annexure H of IS 800 2007, which will be there in page number 138. So here you can see at the last three sections or the last three columns, one is section modulus, which is ZEZ, and the second one is plastic modulus, which is ZPZ, and the third one is shape factor, which is ZPZ by ZEZ. So you don't need to worry about the shape factor and section modulus. Just look at the plastic modulus. That is the value of ZPZ. Now you have to select a section, right? Now you have to select a section which has a plastic section modulus greater than 132. Okay, so let's select the section. So you find out and let me know which section you are comfortable with. So by using IS 800 2007 of annexure H, I am selecting ISLB 200 at the rate 194.2 Newton per meter. So try ISLB 200 at the rate 194.2 Newton per meter. Okay, so this is the section which we have selected. And let's write the sectional properties of this section. So the sectional properties are the sectional properties are, so let's write the sectional properties. One is the depth of the section, which is H, is given as 200 mm, and the width of the flange, which is as 100 mm, and the thickness of the flange as 7.3 mm. Please cross check the values which I am writing. And the thickness of the web is 5.4 mm, and the radius at root, which is R1, is 9.5 mm, and the moment of inertia, that is IZZ, equals to 1696.6 into 10 power 4 mm power 4, and the plastic section modulus of this section is ZPZ equals to 183.34 into 10 power 3 mm cube. And let's also write the value of ZEZ, which is elastic section modulus, which is as 169.7 into 10 cube mm cube. So these are the sectional properties of the section which you have selected. So now the third step is the section classification. Okay, section classification.
Sir, plastic model is 184.34, sir.
184 point. Okay, it is 184. Okay, fine. So the next step is section classification. So how do you do the section classification? It depends on B by TF and D by TW conditions. Okay, it depends on B by TF and D by TW. Remember, these are the fixed conditions. So you have to solve for B by TF, and you also have to solve for D by TW. Remember, B by TF value should be less than 9.4 times of epsilon, and D by TW value should be less than 84 epsilon. These are the fixed conditions. B by TF should be less than 9.4 epsilon, and D by TW should be less than 84 epsilon. So what is this epsilon? Let's find out the value of epsilon initially. Epsilon equals to under root 250 by Fy, where the Fy value is 250. So therefore 250 by 250 will give you 1. Therefore under root 1 equals to 1. Okay, that's clear. So let's find out the B by TF value. So here B is calculated as half of the width of flange. The same thing we have discussed in the compression members also. So B equals to half of the width of the flange, that is 100 divided by 2, which will give you 50 mm. That is what the width of the flange is, 100 mm. Okay, so now let's find out the value of B by TF. So B by TF equals to 50 upon the TF value, which is the thickness of the flange, is 7.3. So this value, if you calculate, you will be getting as 6.849, which is less than 9.4. Right? That's what condition is, 9.4 epsilon, where epsilon is 1. However, that's fine. And next, let's find out the value of D by TW. So D is the value. Remember, D is not the depth of the section. It is not 200 mm. Okay, so the value of D has to be calculated in this way. D equals to total height of the section minus 2 times of thickness of the flange minus 2 times of radius at root. This is the formula which we have used in the compression members also. So therefore D equals to, what is the height of the section? It is 200 minus 2 times of thickness of the flange is 7.3 minus 2 times of radius at root is 9.5. Okay, so if you solve for this one, you're going to get the value of D, which is as 166.4 mm. Okay, so now let's find out the value of D by TW. So that will be 166.4 upon TW value is thickness of the web, which is 5.4. So if you solve for this one, you're going to get the value as 30.81. So which is again less than 84 epsilon, right? So B by TF value is less than 9.4 E and D by TW is less than 84 epsilon. So therefore, the section is plastic section. The section is plastic section. Okay, so most of the times whenever you are solving the problem, it will be a plastic section only. You don't get any other sections, that is compact or semi-compact sections. If you are solving any problem, it will be 99% of the times it will be a plastic section only. Anyways, so the next step we have to find out is check for shear capacity. Check for shear capacity. So how do you check for shear capacity? It depends on the value of VD, right? So it depends on the value of VD, which is design shear strength. So you have to find out the value of VD, which is design shear strength of section. So that is VD equals to, you know the formula which we have discussed in the last class, that is Fy by root 3 into gamma m naught into H into TW. Okay, so where VD equals to the Fy value is 250 upon root 3 into gamma m naught value is taken as 1.1 into height of the section is 200 and the thickness of the web is 5.4. Okay, 5.4. Now if you solve for this one, the value of VD is 141.7 kilonewtons. Okay, so the value of VD is 141.7 kilonewtons. So in the last class, we were talking that VD must be greater than V, right? So VD must be greater than V. So therefore, what is the VD value? It is 141.7. And what is the V value, which is the factored shear force, is 30 kilonewtons. We have calculated, right? So VD is greater than V. So this condition is satisfied, right? The condition is satisfied. So you don't need to worry about this. You can make it as safe. Now you need to check for high shear or low shear case. Okay, so you have two conditions. One is high shear case and the second one is low shear case. So you have to check whether your section falls under high shear or low shear case. So let's keep this heading, that is check for high or low shear. So how do you check this high or low shear case? So in order to check the high or low shear case, you need to check for one value, which is 0.6 VD. So you have to find out this value, that is 0.6 times of VD value is 141.7. All right. So 141.7 into 0.6 will give you 85.02 condition. Now, how will you identify whether a section is high shear case or a low shear case? So you need to refer the previous pages which we have discussed. For high shear case, V value is less than 0.6 VD, and for low shear case. And for high shear case, the condition is V is greater than 0.6 VD. Right, now let's look at whether V is less than 0.6 VD or V is greater than 0.6 VD. So what is the value of V? It is 30 kilonewtons and 0.6 VD is 85.02 kilonewtons. So here it is V is less than 0.6 VD. So when V is less than 0.6 VD, it is the case of low shear. So therefore, it is low shear case, right? So I hope it is clear for all of you how to find out the high shear and low shear case, right? So the next thing which we are going to find out is the check for design bending strength. So let's write the next step. So the next step is a check for design bending strength. Now, how will you find out the design bending strength? It depends on the value of BD, MD. So design bending strength, that is MD, equals to, you know the formula, which is beta B into ZPZ into Fy by gamma m naught, right? So beta B into ZPZ into Fy by gamma m naught. And remember, it's a simply supported beam. For simply supported beam, the value of MD must be less than or equals to 1.2 into ZEZ into Fy by gamma m naught, right? So we have discussed this formula. MD equals to beta B into ZPZ into Fy by gamma m naught. And this value must be less than 1.2 into ZEZ into Fy by gamma m naught. And this is for simply supported beam. So our beam is a simply supported beam only. Anyways, so you need to find out the value of this one. Okay. So here you need to worry about the value of beta B. So for plastic sections, this also we have talked. So for plastic sections, okay, the value of beta B is taken as 1, right? So for plastic sections, the value of beta B is taken as 1. So therefore, MD equals to beta B, that is 1, into ZPZ. Remember, ZPZ value is taken as 184.34. Don't take it as 132. Okay, 132 is the required value, but what is the provided plastic section modulus? It is the section modulus of ISLB 200, the section which you have selected. So ZPZ value is 184.34 into 10 cube, okay, into Fy value is 250 upon gamma m naught is 1.1. Okay, so if you solve for this one, you're going to get the answer as 41.89 kilonewton meter, right? 41.89 kilonewton meter. And remember, this value must be less than or equals to this one, that is 1.2 into ZEZ into Fy by gamma m naught. So let's check and let's find out whether it is satisfying the condition or not. So that will be 1.2 into ZEZ value is 169.7 into 10 cube into Fy value is 250 and gamma m naught is 1.1. So if you solve for this one, it is 46.28 kilonewton meter. So the condition is satisfying. That means the value of MD, which is 41.89, is less than or equals to 46.28, right? So therefore, it is also in safe zone. Now the last step which you have to find out is the check for deflection. Check for deflection. Check for deflection. Now, how do you find out the check for deflection? In order to find out the check for deflection, you need to find out the maximum deflection value. Okay, so let's find out the maximum deflection. So how will you find out the maximum deflection value? It depends on the type of the beam which is given to you. So our beam is a simply supported beam and it is carrying an uniformly distributed load. So a simply supported beam carrying UDL load will have a deflection value of 5 by 384 into WL power 4 by EI. So this is the formula. If you remember the concepts of structural analysis or strength of materials, then you will understand how this formula has come from. Anyways, so let's solve for the maximum deflection value. So therefore, maximum deflection is calculated as 5 by 384 into W. What is this W? It is 40 kilonewtons, right? So take it as a capital W. It is not a small w. I just correct it here. It should be taken as capital W. Okay, just a minute. So it is taken as capital W into L power 4. So where capital W is given in the question, which is 40 kilonewtons. So I'm converting into newtons. Okay, that is 40 into 10 cube into L power 4, right? So what is this L power 4? It is calculated as the length times of 4, right? So the length value is 4 meters, I guess. Yeah, it is 4 meters. So 4 into 1000 cube divided by EI, where E is the Young's modulus, which is the fixed value, that is 2 into 10 power 5, and I value is IZZ. So for IZZ of ISLB 200 is 1696.6 into 10 power 4. So this will give you 9.82 mm. Okay, so this is the maximum deflection condition. Now you need to find out the permissible deflection. What is a permissible deflection? Permissible deflection. So that is delta value. So this we have talked in the last class, that is the permissible deflection to be L by 300. Okay, so the value of L is 4 meters. So I'm converting into mm. So that will be 4 into 1000, that is 4000 divided by 300. So which will give you 13.13 mm, right? So in the last class, what we have discussed is the based on the permissible deflection and the maximum deflection, it is said that the maximum deflection must be less than the permissible deflection. So here it is maximum deflection is 9.82, which is less than permissible deflection, that is 13.13 mm. So the deflection is safe, or the deflection is within limits. The deflection is within limits. So this is how you have to find out the check for deflection. Now, I have said that in the last class, you need to find out two other conditions. One is check for web bearing and the check for web buckling, right? So check for web bearing and check for web buckling. So here you don't need to find out the check for web buckling and check for web bearing. Okay, so most of the times it is not required. Why it is not required, right? That I'll let you know when you have to do the check for web buckling and when you don't need to do check for web buckling. I'll tell you that. So here, if you check down, the value of D by TW is less than 84 epsilon, right? So the value of DW is less than 84 epsilon. Remember, you don't need to do for check for web buckling when the value of D by TW is less than 67. Okay, you can keep this as a note. So note, check for shear buckling or web buckling, check for web buckling is not needed when D by TW is less than 67 epsilon, where epsilon value is 1. So you don't need to bother about that. So remember this condition, when the D by TW value is less than 67 epsilon, then you don't need to solve for the check for web buckling. So this is the entire process of solving or designing a laterally supported beam.